Hello, and welcome to this recorded e-learning on Virtex-6 and Spartan-6 HDL coding techniques part 2. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the design considerations that most FPGA designers will use to get optimum results. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Virtex-6 or Spartan-6 FPGA. This module provides detailed recommendations about creating effective HDL that will provide high speed and save FPGA resources. If you're an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you build a good design that will use minimal FPGA resources and get good performance. These practices are designed to promote fast and efficient FPGA design techniques. After completing this module, you'll be able to code your design so you can infer more of the dedicated hardware resources that you're going to need to get high performance. You'll also be able to avoid the most common coding mistakes which hurt device utilization and prevent designers from being able to infer the most popular FPGA resources. And you'll reduce your dependence on global resets by taking advantage of the Global Set Reset Net, or GSR. If you barely get your design to fit inside the FPGA, the implementation tool's software options may not be as helpful as you'd like. The best solution is to first shrink the register and LUT utilization of your design and to port all functionality to the dedicated hardware resources that you can. To do this, you will need to design appropriately for the dedicated resources. This means correctly writing HDL code that will infer the shift register LUT, block RAM, and DSP slice resources. This module is going to discuss the most common mistakes designers need to avoid in order to infer as much of the dedicated hardware as possible. It is very important to remember that one of the biggest reasons to use a synchronous reset is that certain dedicated hardware resources simply don't have and don't support an asynchronous reset. To infer the DSP resource will require a synchronous reset to be coded. So if the user is going to infer a multiplier, it will have to include a synchronous reset behavior. Unfortunately, synthesis tools cannot infer all possible configurations of the DSP slice, so this will require you in many cases to instantiate the function you want by using the core generator. The DSP slice will allow you to build the most useful arithmetic functions, such as multipliers, adders, subtractors, multiply and accumulate, counters, including counters with programmable terminal count, comparators, shifters, large multiplexers, pattern matching functions, and other components. Likewise, many customers try to infer the block RAM resources and are disappointed when their synthesis tools don't allow them to build what they want. Well, this is a typical limitation of most synthesis tools, but what designers don't realize is that, like the DSP slice, the block RAM does not allow inference of an asynchronous reset. This is because there is simply no asynchronous reset functionality built into the block memory. So, to infer the block RAM's output register functionality, you must make sure you infer a synchronous reset on that flip-flop behavior. Just as I mentioned before, using more of the dedicated hardware resources will improve your device utilization and speed of your design, particularly when you consider that most FPGAs have unused block RAMs and each effectively can implement hundreds of flip-flops. So make sure you are inferring the block RAM with a synchronous reset. Also keep in mind that the easiest way to get the block RAM is to build it with a core generator and then instantiate the core into your design. Another big reason to use synchronous resets is that synthesis and place and route tools are moving towards selectively demoting a synchronous reset from the control port to a LUT input. This is advantageous because less timing critical and low fan-out resets can save the reset port for other functionality. This would also allow the mapper to group unrelated logic into the same slice and improve device utilization and speed. So keep in mind that this could be the biggest reason to code for a synchronous reset. As mentioned earlier, XST does have the ability to move a synchronous reset to a LUT input rather than connect it directly to the reset port of a register. However, currently your results will vary because not all synthesis tools can do that. A good reason to use synchronous resets is that they are automatically constrained when users add a period constraint, which is virtually all Xilinx users. What happens is that the period constraint covers the internal delay paths between synchronous elements, and these paths include synchronous sets and resets. For most designers, this makes FPGA design easier since they have greater assurance that their system's timing reporting is much more accurate. Synchronous sets and resets do not need any special constraints in the design, unlike asynchronous sets and resets. They also do not require any special switches in the timing analyzer for timing analysis to be complete. Synchronous resets are automatically timed and they are inherently more stable. As you may or may not know, asynchronous resets are ignored by the implementation tools. If you use asynchronous resets in your design, you may know that they can lead to disastrous functionality. Inherently, synchronous resets are more predictable. Synchronous resets are less susceptible to accidentally missing timing and race conditions. But the bottom line is that chances are that if you use synchronous resets, your design will work out of the box. This is dependent on the timing analyzer verifying that you are meeting your timing and your functional simulation is working properly. With asynchronous resets, there's much less certainty because there are lots of things that can go unnoticed because asynchronous sets and resets are not covered by the period constraint and require special path-specific timing constraints. As I mentioned, if a reset becomes synchronous, the paths become timed when a period constraint is used. This will increase the number of timed paths, sometimes dramatically. On average, the number of timing paths will increase by around 5%. This is not wrong since you want the design's timing analysis to be correct and help with timing verification. The impact is that the implementation tools will now have more paths to place en route to meet timing. This means more work to do and will cause greater implementation times. But as I said, this is still better than the design not operating at all and having to spend many hours debugging your design. So even though there are some caveats, we will still strongly recommend that you build with synchronous resets. There's simply too many benefits. As an FYI, there have been cases where Simplify will simplify the synthesis results so that it does not take as much advantage of the dedicated hardware when it determines that a design will be harder to meet timing. So it will basically infer very few shift register LUTs and block RAMs, so the design gets built out of additional LUTs and flip-flops to try and get as lean as possible, which can make it harder to meet timing. In this case, make sure that your Simplify result is inferring the appropriate resources, and if it isn't, you need to instantiate the appropriate course to avoid this kind of problem. Altering your HDL and design is the best way to infer a synchronous reset. Some synthesis tools have switches to treat asynchronous resets as synchronous resets. Synthesis tools hate this because their job is to build the functionality you describe, that is, you code, and you're refusing to build the necessary code. Using these switches is not the same as manually changing the code. However, the synthesis tools will put a register on a DSP slice or block RAM if it needs to be synchronous, but does not give the distinct optimization capabilities if the register was coded in the RAM. So this option is not always complete, and we want to be clear, you should not expect that this to be the same as changing your HDL code. Keep in mind that if you don't code for a synchronous reset, in the future another designer will not know that you actually built with a synchronous reset. So keep in mind you may need to create a documentation trail. Also note that some believe that if the global set reset comes to a top of a port and disconnects the port, the optimization algorithms will rip out the reset. Unfortunately, it does not work that way. The synthesis algorithms do that optimization after they have chosen what resources are to be mapped. So you end up with a flip-flop that has an asynchronous reset. If you disconnect that port, remove it, or change it in some way, it does not necessarily change the implementation throughout the design.